Okay, done. Okay, so we've learned that this meeting is being recorded. So again, welcome everybody to this set season of our webinar, and hopefully not the last one. And the previous seasons went very well with good attendance from everywhere in the world. Now we are having another international speaker from the opposite side of the world, from Canada. We've just discussed the climate at that part, which is different, definitely, from our climate. The speaker today is Walaa Moursi, and he's going to present the joint work with our good friend Heinz Bauske. And the talk is about Douglas-Rachford algorithm. Please, Walaa, go ahead.
Thank you. So thank you so much, Alex, Min, and all the organizers for inviting me. And it's my pleasure to give this talk and see so many people that I haven't seen for a while, or so many people that I looked forward actually to know and see. So thank you. So this talk is about Douglas-Rachford algorithm for inconsistent optimization problem. And I added the complete story. So I promise I will tell you at least the complete story for the optimization setting. So what's the deal for inconsistent optimization problem? And this is joint work with Heinz Bauske, which I assume everyone in the audience knows. So in this talk, our setting would be a real Hilbert space, Rn, the space of Sn, little L2, we can allow it. So I would start by recalling what we mean by a monotone operator. So we say that an operator A is monotone if we take 2 points in its graph, and we look at the difference, and the inner product gives us something non-negative. In the simplest form, if you look on the real line and you look at any non-decreasing function, this describes a monotone operator. But if you look at the vertical line, which fails to be a function, of course, it's again an example of a monotone operator. So it could be actually a set-valued relation satisfying this, and this describes a monotone operator. This function, this setting, or this class of operators is interesting from an optimization perspective due to the fact that it actually covered the class of the subdifferential operators of convex functions. It could also have operator that fails to be subdifferentials or gradients, like the skew-symmetric operators, but at least it has this class, which is very interesting to us from an optimization point of view. So in this talk, whenever we refer to A and B, we talk about maximally monotone operators, and the problem that we will talk about in this talk, and we will try to actually see the behavior of the method Douglas-Rachford when solving, is the problem of finding a zero-bus sum of two maximally monotone operators. So we want to find an X that solves this inclusion. So basically, we're looking for an X in X such that 0 is in AX plus BX. Remember that these operators could be set valued, so that's why we have an inclusion. So AX and BX are possibly sets. So we are looking here as a Minkowski sum of two sets. One method to solve such an inclusion when A and B are maximally monotone operators is the Douglas-Rachford method. And how this method operates is via iterating the so-called splitting operator T. So the operator T, which is a function of A and B, so we care here about the order. I'll drop the subscript later, but it is defined in terms of what we call the reflected resolvents RA and RB. So RA is just 2JA minus the identity, where JA is what's called the resolvent of the operator A, which is defined through this inversion. And what we look at here is the composition of these two operators. So this is the problem that we cared about in general. And how it ties to optimization is the fact that a central problem in optimization is to minimize the sum of two functions, f plus g. And we will see now that this can be written more or less in the form of solving that inclusion. Because if we are in the ideal situation where we have two smooth functions, then from Calc 1, we know that we are actually looking for critical points of the sum. And this means that we look at the gradient of the sum, which is the same as the sum of the gradients, and try to set this to be 0 and find x that solves this identity. Now, if we go more general and we are in the less pleasant situation where the functions are not necessarily smooth, then we no longer have the luxury of working with a gradient, and we need to work with a more general structure of the so-called subdifferential operators. And then we start losing some privileges. So the first thing is we no longer can talk about an equal sign, because subdifferential operator is a point to set operator. So it's very possible that this is mapping x to a set and not a point like the gradient. And therefore we have an inclusion here. And the other luxury that we lose is this equal sign that we get here is no longer here for free. We need some sort of constraint qualifications so that we can say that the subdifferential of the sum is the sum of subdifferentials. So we're going to, if we look at this, 0 is in the sum of this set plus this set, then you can see this as ax plus bx. And therefore, because those are maximally monotone operators, whatever algorithm can find us 0 of this sum would work to find a 0 of the sum of those two subdifferentials, which under some mild assumptions would serve as a minimizer of f plus g. So this is the problem that we care about. And again, I will step back and say, okay, the sum of two functions. From an optimization perspective, it's nice actually to find the sum of two functions, but how important this structure is, it's actually very nice, because we can use this structure to convert constraint optimization problem to unconstrained. But of course, so the price is you need to deal with sum of two functions. And the trick that we use in this case is the so-called indicator function. So the indicator function of a set U is a very nice function. It actually favors the points in U and gives them the value 0. 0 is not always a nice number to be assigned to, but from an optimization perspective, if you know what it does to the points outside, you will really appreciate that it gives these points 0, because whenever the point is outside the set, it gives it the value plus infinity. And therefore, if we want to minimize a function f over a set U, then we can write that as minimizing the sum of f and the indicator of the constraint. And therefore, you can easily see that no minimizer can lie outside the set U, because whenever it's outside the set U, the sum would have the value plus infinity. So very nice way of writing it. But again, there's no free lunch, and the price we pay is to deal with sum of two functions. And we could go even more special and look at finding a point in the intersection of two sets, which again can be written as minimizing the sum of the indicator functions of the corresponding sets. And again, if we are in the intersection, both functions will have the value 0. If we are in one set but not in the other, then the sum is plus infinity. So definitely the minimizers would be the points in the intersection. So what is known? Classically, the method is a very beautiful literature about the convergence analysis of the method, and it's very well known starting in 1979. So the method works as follows. This is the operator that I'm talking about. And what happens is that we start with a starting point x0, and then we construct a sequence x1, x2, x so on by iterating t. So x1 would be t of x0, x2 would be t of x1, and so on and so on. So we apply t recursively. And because t is an operator that has nice properties, which is called firm non-expansiveness, iterating this t would behave nicely and give us a convergence sequence as long as the fixed point set of t is non-empty. And this assumption that the fixed point set of t is non-empty, thanks to a result by Combet, is equivalent to a plus b has a 0. So if a plus b has a 0, the fixed point set of t is non-empty. Because of the nice property of t, I can iterate t, generate this red sequence, which we call the governing sequence. And that sequence would do fantastic. It will converge weakly to a fixed point. Now, we have to be careful because this fixed point is not necessarily a critical point that we are looking for. However, this fixed point has something to do with the critical point that we want to reach. because if we hit the set of fixed points by JA, this result by Combat in 2004, then we will recover the critical points that we need. And that actually shows us the importance of the second sequence, the green one, which we call the shadow sequence. So what happens is that this red sequence here, Xn, we shadow it with the resolvent of A, and the new green sequence in this case would be the one that would converge weakly to the critical point that we look for. So that was actually in the general framework of monotone operators. Again, from an optimization perspective, we care about functions. So everything actually translates nicely to functions. Suppose we start at x0, and the sum of the subdifferentials has a 0. Then that's the governing sequence that will converge to a fixed point, not necessarily a critical point, but the shadow sequence, in this case, the resolvent JA, which we had on the previous slide, is just the proximal point map operator or the proximal point mapping associated with the function f. And we recover the desired set of critical points by hitting the fixed points of T by prox f, which leads to the result that the shadow sequence will give us a point in the set of minimizers of f plus g. So observe that before I talk about anything, I started by this assumption, the set of zeros of the sum is non-empty. And here's a visualization of the method. So in the simplest form, as I said, we can look at this as actually finding a minimizer, like finding a point in the intersection of two sets, which is the same as minimizing the sum of the indicators. So I want to minimize the sum of indicator of the two lines u and v. I want to find this point, a point in the intersection of the two lines u and v. So in this case, T, the resolvent JA, JB, or the prox operator are just the orthogonal projections onto the lines. So they're just the projection onto V and U. And this is what the operator T looks like in this case. And here are the two sequences that I talked about. So we have the governing sequence, the red one, which starts at x0, and I apply T recursively. So I start spiraling towards a point, which is actually on this vertical line here, clearly not the point in the intersection that we look for. And as I said, we need the shadow sequence. The shadow sequence would be the one that starts shadowing these points or projecting those points onto the blue line, PU of T and X. So each of these iterates, I start projecting them, and that would give me the blue sequence here, which will converge at the end at that point in the intersection. So that's a visualization of how the method works in a very simple, nice framework where we have linearity and convex feasibility, so we can visualize everything. Okay. So I copied and pasted the earlier slide, so I won't go through all that, but I said earlier that we start assuming this, and then based on that, we get very nice results. So what if we don't have this assumption? What if the set of zeros or the set of critical points is empty? Now, let me just show you what does this mean in a visual way. Those were the two lines that I started with, but I did something mean here. I actually tilted one of them a little bit, so the two lines are no longer intersecting. So there's a gap here between the two lines, which I like, that's the square. So V and U are now tilted. And what happens is that the sequence in red that was actually theoretically converging is no longer converging. And even theoretically, we know that it will not converge. In fact, this sequence here diverges to infinity and more. However, the blue sequence, which shadows this terrible sequence, remains bounded. Again, this was known theoretically. And I will actually talk about this more in details, but visually, this is what we are at. So the thing is, this means that we don't have minimizers. We don't have minimizers. As I said earlier, existence of minimizers is equivalent to existence of fixed points of the operator T. So we don't even have fixed points to talk about. And the first thing actually to proceed is we asked ourselves, what would be the right framework to talk about? Because the problem does not have a solution. And that's why I said like the generalized framework of the normal problem, because the original problem does not have a solution. So we need to actually look at something that's more meaningful, because what we are looking for, if we don't have solutions, we need to define something that we're looking for that would generalize the set of solutions that is now empty. Let's look at a more general framework. So observe that the absence of fixed points means that 0 is not in the range of identity minus t. Otherwise, if 0 is there, it means we have a fixed point. There's something really nice about this set. If we close it up, it's non-empty closed-down convex, because actually this operator is maximally monotone, and therefore its range is non-empty closed-down convex set. And therefore the projection onto this range is well defined. And we started from there because, okay, we don't have 0 there, but let's at least look at the smallest, the element with the smallest norm in this set here. And we called it V. So we look at the minimal displacement vector in the set of the closure of the range identity minus t. And using that vector, we start defining the so-called normal problem. So, okay, we start thinking, okay, maybe A plus B does not have a solution. But if we cleverly perturb the graphs of these operators, maybe they meet somehow, and we can talk about a more general problem. So we define the normal problem, which is the problem that's obtained by perturbing the graph of A and B. So one graph would be perturbed vertically and the other will be perturbed horizontally, because here we are perturbing the range of A, whereas here we are perturbing the domain of B. And the corresponding generalized set of solutions, or what we call normal solution, is just the set of zeros of the new sum problem. In fact, the word or the name normal problem didn't come out of nowhere. We actually have roots in linear algebra. So suppose that we are working on Rn, and let's assume that the symmetric part of the matrix, the square matrix A, is positive semi-definite. This is exactly equivalent to saying that A is actually maximally monotone. And let's look at solving this linear system of equation, Ax equals B, which we can write as Ax minus B equals 0. Now that's an A, and we can actually define B to be the shift of the 0 operator, taking everything to the vector minus P. And in this case, we can look at this problem as finding a 0 of A plus B. And if B is not in the range of A, then the set of zeros is empty. And in this case, we can show that the minimal displacement vector that we just defined here is actually the projection of minus B onto the orthogonal complement of minus range A, and onto the orthogonal complement of range A, and the normal solutions are just the least square solution. So again, that was the motivation behind the static framework of the normal problem, but there was another motivation because there were some promising results earlier. So let me remind you that when the set of zeros is non-empty, theoretically from fixed point theory, this is not something that we proved, it's actually known in fixed point theory that T and X, so the iterates will diverge to infinity and 1. However, if we assume that that vector V is attained in the range of identity. So by definition, V is in this set, but I'm going to be a little bit more greedy and assume that it's attained. So it's not just in the closure, but it's attained in the set itself. I would say that the most motivating result was what appeared in 2003 in the work by Bautka, Combat, and Luke. So in that paper, they worked with a convex feasibility setting. They looked at f and g, or indicator functions of two sets. And despite the terrible behavior of this set, of this sequence, they were able to show that the shadow sequence stays bounded. And once you have a bounded sequence, you can talk about the weak cluster points. And guess what? The weak cluster points, not just that the sequence is bounded, but the weak cluster points are actually very well behaving. They actually serve as normal solutions. So they solved the right problem that we talked about. Now, based on that, in 2015, the first positive result, the first positive convergence result was in 2015, where we proved strong convergence of the shadow sequence, was a linear rate and identified, and there's a identified limit when the sets are closed affine subspaces. And now there was a joint work with Min. So you might recall this Min. We have this 2015 paper, and then followed by another paper in 2016, where we talked about convex feasibility problems. So we were able actually to prove the full weak convergence in the setting where both F and G are indicators of non-anti-closed convex sets, not necessarily intersecting. So we were able actually to go from boundedness and weak cluster points are located to much more general setting. I have to say to a much more general or much more beautiful result of weak convergence. I have to say that going from here to here was not easy. And maybe you recall that, Min, because the thing is, we don't have fixed point. And the classical fair monotonicity results and all that was not applicable there. We really needed to come up with something new and more general so that we can actually build our analysis on. And now, here we stopped for a while. We were not able actually to make more progress because the very next step was, okay, that was a deal for two indicators. The geometry in the indicator functions case is actually very beautiful and very helpful. Aside from indicator functions, when you go to two functions, it's not easy. But then until 2019, we started, okay, maybe we can do something, and we were able to do something of minimizing a convex function subject to linear constraints. So that was the very first progress that we made outside the convex feasibility setting. But the problem is we heavily used linearity here. So the result was really nice because we were able actually to show that we converge to a normal solution under this assumption here. So we assume that 0 is in this set here. I will comment on that later, but let me tell you that that assumption in that paper was sufficient to prove convergence. It wasn't clear for us how crucial this assumption is until the work that I'm presenting on today, where we prove that it's not just sufficient, but it's actually necessary. So it's a characterization when the shadows stays bounded. So that's why I'm saying, like, we're going to talk about complete story. So generalizing from here was not feasible. And in fact, the work that we have today, even though it was inspired by all these results, it did not go from generalizing these results, because here linearity was actually bringing a lot of things that we haven't seen clearly, because we thought, like, how would we generalize this linear? How would we work with this? So it wasn't actually very helpful to look at it from that perspective. And here's an example of the convex feasibility case. So two sets do not intersect. Here is the starting point, and that's the governing sequence. It will not converge. It will diverge to infinity in norm because the sets do not intersect. But now we look at the shadow sequence and we start shadowing. So that's the shadow of x, and that's the shadow of tx, and that's the shadow of 2t square x, and so on and so on. And interestingly, just for this particular instance, we get finite convergence and we converge to this point. So it's a best approximation solution. There were related works based on that. So I would say that the most important result that we relied on in most of our to make any progress in most of our convergence analysis is the fact that we were able to get formula for the range of identity minus t. There's more general formula that involves monotone operators, but for two functions, that was the formula that we got. And in 2017, 2018, based on this formula, Riedelin and Yin proposed a method based on Douglas-Rachford, where they were able to identify infeasible and bounded in pathological conic and convex optimization problems. And in 2018, Banya, Golet, Stellato, and Voigt did similar analysis for ADMM, which is actually a form of Douglas-Rachford. And in 2020, Banyak and Legueres and Banyak had a couple of nice papers where they extended some of the geometric results on our minimal displacement vector V to more general framework. So at this point, the question that we started with ourselves is, starting with an x0, what can we say if A and B are maximally monotone operators, not necessarily functions or subdifferentials of functions, sorry, but nice maximally monotone operators. And when I say nice, there are classes of maximally monotone operators that contains subdifferentials as proper subclass. but they are not as bad as the very bad behaving operators like the skew guys. Now, being more specific, inspired by the Bausch-Combat paper, as a first step, can we characterize when the shadows are bounded? Not in the convex feasibility setting, but maybe in the monotone operator setting, or at least for functions. And if we can answer step one, first step, and we know when the shadows are bounded, can we locate the cluster points? What can we say about their location? Can we prove their convergence? So to make progress, we need some assumptions. And again, I said I'm going to tell the complete story, and I still believe that that's a complete story. So I'm going to comment on these assumptions later. But assumption one is actually fairly sensible, because we are going to assume that this is true. You would probably stop me and say, like, you prove this. Yes, we prove that when X is finite dimensional and A and B are nice. By nice here, subdifferentials is good enough. So if we have subdifferentials and we work in finite dimensional spaces, assumption one is actually for free. We don't need to assume it. Okay. Now, under assumption one, there's beautiful, beautiful geometry going on here. So this is assumption one, which again, as I said, is true whenever we work with subdifferential operators. And I'm going actually to talk about two baby vectors, VD and VR. So VD and VR are basically the minimal norm elements in this set and this set. So I'm looking at the smallest norm element, or the element with the minimal norm in these two sets. And if you look at this structure here, I'm looking at the projection or the minimal norm element in the Minkowski sum of two sets. I'm going to use this fact to locate this vector in the polar of the recession of the individual sets. So using this fact and allocating U and V to be the right sets here, I was able to locate VD and VR in these sets here. So I'm going, what I wanted to carry from this slide is that I know now something about the location of VG in terms of the polar of the recession of the domain of A and polar of recession of the domain of B. And the same for VR. So that was one piece of location that we were able actually to show. Now, the second part is, again, I am going to find supersets for these sets where that would give me further information about the locations of the baby vectors VD and VR. So this inclusion here, once we get this blue one, everything else would follow easily. And the reason is, if you believe this, and this is true for any maximally monotone operator A, then it's definitely true for B. So that would give me this inclusion. And if it's true for A, it's true for its inverse, because if A is maximally monotone, A inverse is maximally monotone. So that would give me this part, because the domain of A is the same as the range of A inverse. So, sorry, the domain of A inverse is the same as the range of A. So I'm going to quickly do a sketch of the proof of the blue inclusion. Now, it's a sketch of the proof because it uses the deep and beautiful result in monotone operator, the Mercier theorem. So this inclusion is always true. From here to here, we use the Mercier theorem. And from here to here, we use the fact that A is maximally monotone. So this is the same as A. And if we follow the green part, we get that this inclusion holds, which if we look at the definition of the recession cone, this just tells us that the closure of the range of the normal cone of closure dom A is just in the recession cone of the closure of range A. So we get this first inclusion here. Now, the second part to finish the proof hinges on a deep result by Zarantanello. So using the Zarantanello result, we have the closure of the range. This set here is just the polar of the recession cone of the domain of A. So if you look at this set here and with this equality, then this means that this set is included in this set, and that proves our first claim. And as I said, everything else will follow. I don't want you to actually go deeper into this, but that would actually give us a control on the location of the baby vectors VD and VR much better. Those 4 locations, I won't dig deep into them, but if you make the right selection and use the definition of being in the polar cone and in the cone, we learn that this inner product in green, one time we get it non-positive, one time we get it non-negative, and therefore we have no choice but believing that the 2 vectors are actually orthogonal. And again, the gray item is an auxiliary item, but based on the green one and filling in some details using the definitions of V, VD, and VR, we're able to show that the vector V, the minimal norm element that we cared about, the key to define our normal problem, can be written as or decomposed into the sum of these 2 orthogonal nice vectors. So these 2 are actually key in our analysis. This is very beautiful geometry. I have to say that we showed this in the linear case, but the proofs were highly linear. You can imagine, like, orthogonality, you get it for free. There was a lot of things hidden, so we were not able to go from generalizing these results right away. Now, that was on the static side. We get beautiful geometry going on, but we want to know what's the deal for the sequences, because this is what we care about. We want to know what happens in the dynamic world, what happens in the dynamics, what the sequences does. So this is known. What's here is nothing new. This blue limit is classical from fixed point theory, nothing new. These 2 identities comes from the fact that this is just, if you look at this, this is identity minus T acting on Tnx. And then I just plug the definition of DR operator, identity minus T can take this form or this equivalent form. And this is what I plugged here. So nothing to worry about. But based on that, we were able to obtain this proposition, these 2 items. I would read only the first item. The second, I would say it's a dual version of it. So what you see here is the shadow sequence. I'm looking here at a limit of the difference of 2 consecutive terms of the shadow sequence. And if you know the limit of 2 consecutive terms of the sequence, you can say something about its asymptotic regularity behavior. So looking at this item, we know that this sequence is asymptotically regular if and only if it goes to 0 here, which means if and only if VR equals 0. So here we can see the necessary condition of the sequence to converge. Remember, I said earlier, I don't want you to recall what the condition was, but I said earlier that in the latest result we had before this work, we had an assumption that we needed to have as a sufficient condition, but it wasn't clear to us how crucial it is. And now we were so happy to see that it's actually a necessary condition as well. So it's a characterization. And this is a dual version of it. So this is a primal shadow, this is the dual shadows. Now the second assumption. So what's the second assumption? We're going to assume that V is attained in the range of identity minus T. And again, I'm going to comment at the end how crucial this is. So why this assumption is important, because in fact, and I omit the proof here, but the attainment of V is equivalent to having the normal solution or the generalized solution set non-empty. And this is, again, very sensible, but I will convince you further how sensible this is. But this is sensible because, okay, the problem doesn't have solutions, but at least the new generalized problem should have a solution, right? Now, under this assumption 2, we can see some fair monotonicity coming along the way, which is actually beautiful. Everyone who is familiar with splitting methods know how beautiful it is to see some fair monotonicity there. So working in the product space X times X, in assuming A2, assumption 2, that V is attained. Again, I won't read the details, paramonotone and all that, but this is in the framework of maximally monotone operators. This paramonotone assumption implicitly covers subdifferentials. So again, if we are in the optimization world, then this is nothing to worry about because we get it for free. And what we learn is looking at this sequence. So this is just a shift of the sequence by this point in the product space. And the sequence we are looking at in the product space is this and this. And this is a fair monotone sequence with respect to Z times K. Z is the normal solutions that I talked about, or the generalized solutions. this problem has a dual problem. So the primal part comes from here, the dual part comes from here, and in the product space, this is fair monotone with respect to primals times duals. And fair monotonicity right away gives us that the sequence is bounded. So we learn that this sequence is bounded, and here comes the most exciting part. Now, that is the primal shadows, that's the dual shadows. Let's just focus on the primal shadows for now. I won't talk much about the duals. In the paper, we work with primal dual, but let's look at the primals that we care about. Now, this is bounded. Therefore, the primal shadows, which is this part, would be bounded if and only if VR is 0. So now we have a characterization when the shadows are bounded, which is actually beautiful. This is exactly what we were about. I mean, that doesn't finish the story because we are just at the boundedness. We don't know about the clusters, where they are, but at least we know that we are heading where we wanted to go. So right now, no longer operators, I'll drop to optimization settings. So from now on, we are going to assume that F and G are proper lower semi-continuous convex functions and set A and B to be the subdifferentials of F and G. And the last assumption, and again, the last assumption justifies itself by what I just talked about. So assumption 3 assumes that VR equals 0. And VR is 0 if and only if, because remember earlier we have V decomposed into VD plus VR. So if VR is 0, this means that V is VD. You remember that decomposition earlier. So this means that V is just VD. And what is VD? It is the projection of 0 onto the Minkowski difference of the domains all closed. And because we're in the optimization settings, those resolvents becomes the proximal mappings of prox operators. So I'm going to abbreviate the proxies just for more decent formulas. So prox F star would be PF and PF star, prox G, PG, and the reflected prox RF. And the DR operator will take this form. So there's nothing here magical. I'm just actually putting like the optimization tools instead of the maximal monotone operator tools. How do we get convergence? Because I said I'm going to tell the complete story. At the end, I will comment on the assumptions, but how do we get convergence? In 4 steps, I'm going quickly to comment on that. So the first thing is we refine the definition of Z. We use the fact that VR is 0 and we simplify Z. And because Z is non-empty, under the assumption that V is attained, it's equivalent to Z, the generalized solution is non-empty, we can prove that Z is the critical points of the generalized problem. And we can prove that the critical points are exactly the minimizers. In general, and that was actually a new part that we struggled with a bit in this work, because in general, critical points are always subset from the set of minimizers. And it's possible that it's a proper subset. But what was really interesting, and this for any two function, is it can only be a proper subset if it's empty. If it's non-empty, then they're equal. And that was actually critical in our proof. Step 2, the boundedness of the shadows. Now we proved it in a more general framework of maximally monotone operators. So we just get this for free from the more general framework of maximally monotone operators, along with the assumption VR equals 0. Remember, that was actually an if and only if. So VR equals 0 is necessary and sufficient for the boundedness of the shadows. And now we have a bounded sequence. We can talk about its weak cluster points. We were able to locate the weak cluster points to be the minimizers of this. And now we located it to be the minimizer. So we are in the right set. Finally, we want to prove the full convergence. What happens is we combine the boundedness result along with where the cluster points are, and we use the fact that we have fair monotonicity with respect to a certain set, along with some fair monotonicity classical results, and we were able to obtain the convergence. And I will go through some proofs high level. So step 1 was refining Z. I won't prove that, but I will just show you what happens there. So the generalized solution set is the solution set of the perturbed problem. So instead of looking at the 0 of subdifferential f plus subdifferential g, we had the perturbation of the graphs of f and g, vertical perturbation, horizontal perturbation. So that was in the general framework what the generalized solution set looks like. However, because we are assuming this necessary and sufficient condition for the shadows to stay bounded, under this condition, this minus v gets magically absorbed and z simplifies. So we no longer see this minus v, and z simplifies as if we only perturb the graph of g horizontally. We don't need to touch the graph of f. So that was the first refinement. The other thing is that under this assumption, we were able actually to show that if the critical point set or the set of critical points is non-empty, then it coincides with the set of minimizers. So again, classically, we know that Z is always subset from the argument. Critical points are always subset from the argument. However, it turns out that we can only get proper inclusion if this set, if this Z is empty. If it's non-empty, then we can get proper inclusion. Step 2 is the boundedness of the shadows. I talked about this high level because we had this sequence. As I said, that was actually a shift. I don't care about it. If this is fair monotone, then dropping the shift would not affect my boundedness, and this sequence remains bounded. And in the optimization setting, this JA becomes PF, and that's PF star. VR is 0, so we no longer see this term, and this sequence becomes this sequence. And therefore, we learn that this is bounded. And even better, we learn that this sequence is fair monotone with respect to Z times K. Step 3 is to locate the cluster points. So I put here the full proposition, but I don't want to actually overwhelm you, or even like for the purpose of the talk, I only need this item in this item. So the first item says that this is bounded, and I kind of like went through that in the previous slide because this is just a byproduct of fair monotonicity right away. And the cluster points are minimizer of f plus g. That was part of the meats of this work. Actually, this was like non-trivial amount of work to reach to this conclusion. So this part of the proof was actually highly non-trivial. This is a consequence of item 1. I won't go through it. It's more technical. But item 3 is really beautiful because it also tells us that we get value convergence, because that's actually really nice to know, because it's if Z bar is a weak cluster point, then we get value convergence to f of Z bar. And then the last step, the full weak convergence of the shadows. So again, I care about item 1. Item 2 is direct consequence, more technical stuff, so I won't go through anything about item 2. But just believe me, once we prove this one, and with a little bit of work, we can get item 2. So I care about item 1. That is the primal shadows that I claim that it converges weakly to a generalized solution or normal solution. How do we show that? Well, we show that the sequence is fair monotone with respect to Z times K. What is Z? Z is a generalized solution set of the primal problem. K is the dual part. We won't work with K, but the thing is, like, we get fair monotonicity in the product space only, and that's why we need to restrict ourselves there. We don't get fair monotonicity. I can say that this is fair monotone with respect to Z, and this is fair monotone with respect to K. We just need to work with primal dual. Now, how do we prove full convergence? Well, I pick 2 cluster points, and if we're lucky, we can show that they coincide. And this is what we exactly are going to do. I take 2 cluster points, 2 weak cluster points of the shadow sequence. And on the one hand, in step 2, we proved that they are both in Z, and therefore it's clear that their difference is in Z minus Z. But classical fair monotonicity result tells us that if we take the difference between in 2 cluster points here, that would be in Z minus Z perp, which means that we have no choice but having Z1 minus Z2 is 0, which means that we have 1 cluster point, and that shows us that the sequence converges weakly. And that finishes the proof of convergence. And I'm almost done. I have a few minutes to say why I said, or I claim that this is a complete story. although I actually put 3 assumptions. I talked about assumption 1, assumption 2, and assumption 3. So let me at least defend myself and say that that was not violating or actually contradicting my claim that this is a complete story. So assumption 1, as I said, as long as you're comfortable staying with finite dimensions, it's more than enough for optimization settings. So when I say that this range is equal to this is always true if we have 2 functions. So the only thing is that if we go infinite dimensional, then there is room to say stuff there. It's not like the results are not clear what's going on in infinite dimensions. Assumption 3, VR equals 0. I think I convinced you, at least if you believe the proof, if you go through the paper, I said like about VR equals 0, that was a necessary and sufficient conditions for the shadow to stay bounded. And we can't do anything if it's not bound. So because it's necessary and sufficient, I hope that also this convinces you that we can't do any better. Now, what about assumption 2? And I know that I didn't go like sequential A1, A2, A3. I went A1 and A3 because it was easy to defend A1 and A3 on one slide, but A2 is a bit of a story. So we needed to assume attainment of V. And what I'm saying right now is if we don't have A2, we can't say much about the sequence. And the reason is if A2 fails to happen, we can't conclude anything about the shadows. And I illustrate that with 2 examples where A2 fails and the shadows converges in one step, and A2 fails and the shadows below to infinity in one. So the example, the positive example is actually very easy. Stay with the real line and look at minimizing the minus square root of x subject to x equals 0. So very simple setting. And of course, minimizing the minus square root of x, sorry, the minus square root of x, sorry, I draw it. The minus square root of x subject to x equals 0, the set of argument is just 0. But because the domain of the subdifferential of f is 0 and that of g is the strictly positive part of the real line, we learn that z is empty because z is just as the zeros of subdifferential f plus subdifferential g, and the domains do not actually meet. So the set of zeros is actually a subset from the domain of the sum, which is empty. So z is empty. Now, what is the closure of the range of identity minus t? If we look at this by definition, we get that this is just the non-negative ray, and therefore v is 0, but it's not attained. It cannot be attained, because if it's attained, then z is non-empty. That's an equivalence, if and only if. So we get v here is 0, but it's not attained. However, despite that this is the same as saying that A2 fails, look at the shadows. I don't know what Tn does, no matter what it does. The prox of f here is an indicator function, the subdifferential of the normal cone, the prox is the projection. So you're projecting onto a singleton. No matter what happens, you always, no matter what Tn is, you always project onto the 0. So the shadow sequence converges in one step. So this is a very positive example where A2 fails, but the shadows do the right thing and gives us the right thing. Now, A2 fails and the shadows are unbounded. So here we are going to recycle example by Ryu, Leo, and Yin in their 2019 paper. So suppose X, we work in R3 this time to get our counter example, and we take K to be the ice cream cone, and F would be the indicator of that cone. G would be a very nice function. It's a linear function plus an indicator of the subspace x2 equals x3. And now to make progress, because it's not very easy to calculate things in closed form with projection, things and projecting onto the cone. So we need to start as a very special starting point. So we start at the starting point where x3 is 0. And we need to fill a lot of details here. But after filling in the details, we can show that v is 0, but it cannot be attained. So we are actually in the setting where A2 fails. And because it's not attained, as I said earlier, and this is like a result that we proved, v is attained if and only if z the generalized solution is non-empty. So if B is not attained, the generalized solution is empty. Now, Z is empty. However, the minimizers of alpha plus G is non-empty set. So the set of minimizers is this set, which is the intersection of ice cream cone with this ray, with this subspace here. And of course, this is exactly what we are about. We want a problem where the set of minimizers is non-empty, the set of critical points is empty, and then we want to see what happens. And it turns out that the shadow sequence, which is in this case the projection onto the cone, the features of T, and here there is a lot of details and work to show to get these in closed forms. It turns out that it diverges to infinity and on. So I defended my three assumptions, and I think this finishes the story for optimization problems. I hope that you like the talk. I didn't put many references because there are tons of references actually. So I just put the paper, and if you're interested, just go to the references in the paper. There's a lot of references there. And thank you for inviting me again.
Thank you very much, Walaa. Very interesting presentation. And I would say very professional presentation. Everything has been very well organized, very logical, beautiful slides. And the speaker obviously liked presenting. And we also like such situations. And we also like complete stories. You promised a complete story and you presented a complete story.
I hope so. I think for optimization problems is Min can correct me. I mean, I think Min actually, I had the pleasure to collaborate with Min in one of the parts of this work, and I think he might have some insights about this as well.
As an outsider, for me, it looked like a complete story. So I suspect that there should be questions from the audience. Maybe Min wants to comment something as an insider. So anyway, do we have any questions, comments, please? No, it looks like the members of the audience are so impressed by the presentation that they are not brave enough to unmute themselves. So now Min is brave. Min?
Yes. Thank you, Walaa, again for the very nice talk as always. Yes, we love a long story about inconsistent problem, right? We know that even at the very first glance, people might think that if the problem is inconsistent, so there is nothing to do. But actually, as Walaa show, you can see that is we still have much thing to do, right? Yes, yes, it's my pleasure to to have some joint work with Walaa as part of this big project in inconsistent problem with Douglas-Rachford algorithm. And Walaa, I have maybe a naive question regarding the assumption A1. We know that in finite dimension, so it's it automatically certified, right? But how about in infinite dimensional? Do you have example that did assumption verify in infinite dimensional, but not finite dimensional?
Okay, so let me comment on that. So stay tuned for an upcoming work that's related to infinite dimensions. Yeah. But let me tell you that it's not easy. I tell you what the problem is. In the 2015 paper where we had this result for finite dimension, the problem that this result highly relied on the relative interior calculus, which we know that it falls apart in infinite dimensions. Like we don't have a counterpart of the relative interior in infinite dimensions. And then based on that relative interior, there's also like the calculus of the so-called almost convex or nearly convex set. So all that does not carry over in infinite dimension. That's why we don't have a counterexample, but we actually were not able to make progress. as I said, stay tuned for some progress on this, but it's not an easy thing actually to finish in a paper, I would say.
Yes, I understand that. Yes, in infinite dimensional is.
I mean, the structure, note that the sets domain are because these sets are not actually convex. Their closure is convex, like the domain and the ranges. Their closures are convex, so their interior is convex, but they are not necessarily convex. Right. So working with these sets is not actually very easy. And in infinite dimensions, we were able to make progress easily just because we relied on the relative interior calculus that's well developed by Rockefeller. But going outside finite dimensions is not easy.
Yes, I agree with that. Yeah. Okay, thank you.
No. I have a suggestion relative to that. That was a really interesting discussion. I've been wondering what some of the use is of these infinite dimensional calculus type things, because I've been looking at this at some work that Nam has done. Nam at Portland State University. And you might actually find this interesting. It's not published yet, but it's up on Archive, where Nam and Boris Murtakovich and Kung and Sandine, I'll paste the reference in the chat. They developed the subdifferential calculus in infinite dimensions based on a quasi-relative interior condition for polyhedral sets with, you've already seen it. Okay.
I'm not aware of this paper, but we have looked at there is a paper by there is a paper by Luce and Borwein, and there's there are papers by Zolinesco as well for the quasi-relative interior and all but the problem is that none of these structures actually would extend the analysis that we used for relative interior. It doesn't actually carry over. For example, if you have in the relative interior where you look at the relative interior of C minus D, two sets, or plus D, you get this, which is, minus. This is something that we actually used intensively. It doesn't carry over. The fact that if you have an almost convex set or nearly convex set, you get that the closure of the relative interior of C coincide with the closure of C coincide with the relative interior of C is the same as the relative interior of its closure. All these properties do not carry over, even with the quasi-relative interior or the I think this is the best one that we could have worked with, and we tried it and it didn't carry over, unfortunately.
Yeah, it's a headache.
It's not easy. It's not easy.
So one last very short question.
Sure.
Are there short questions from the audience? Then we finish here. Thank you very much again, Walaa, for your very interesting presentation. We are all now tuned in and looking forward for the continuation of this big project. A small portion, I guess, of this big project is already in Ballarat. So we are all looking forward to what's happening. Min has unmuted himself. Do you want to say something?
Thank again, Walaa, and thank all the audience.
Thank you so much for the invitation. And I don't think Heinz is here, but I would love to thank Heinz, who brought me to the love of this inconsistent problem. And since then, I own a few nights actually where we both kept sending emails until 3 a.m. and 4 a.m. because of these problems along the years. So Heinz is not here, but I have to admit that I owe him all the fun I had with these projects with him and with the problem itself. The problem is so beautiful. So thank you.
Then please also send our thanks to Heinz for keeping track of such big projects and for delegating members of his big team to Ballarat. Okay, so thank you very much. Our seminar is closed for today, but we are going to continue next week, right? And everyone is welcome. Also, tell Heinz to join us occasionally, maybe also as a speaker, presenter.
I think he had constraints today, if I remember correctly. that's why I think he had some constraints or some others, because it's for us here, it's quite late.
Yes. Yes.
Yeah, this is true. But this is going to change in a month.
Yes, actually, I also sent the announcement to Heinz and so on too, but they have some constraints.
It worked well for me because at least I will get. His are now actually almost sleeping, hopefully. So it worked really well for me.
If it works well for you, feel free, or you are welcome to volunteer for another presentation.
I would love to, definitely.
Just go ahead, volunteer, send your suggestions, send your abstract, and we will consider. Okay, so thank you, everybody, and if possible, see all of you next week.
Thank you so much. Thanks, everyone. Thank you. Thanks, Elsa and Yanis, Leon, Julian, Nadia. Thank you, everyone. Bethany, thank you.
Okay.
Bye.
Bye-bye.
Hey, thank
Bye.
you all.
Thank you.
Thanks, Walaa.